Welcome back. So just a few announcements. I think you've seen all the LaLima posts, but homework 3 has a flexible due date. There's a poll right now, and it seems like most people want it after spring break, but you can keep on voting if you want. Keep in mind, I won't be around for spring break. I'll be on spring break myself, so I won't be able to answer any questions, but you will have everything you need to do for homework 3 beforehand. And the exam covers all the material on homework 3, so I recommend doing homework 3 anyways before the exam, since the exam will cover that material. So you have a week to do the exam. It's due on the 7th, I think. It's a multiple choice on LaLima. And it's open notes, open internet, open everything. Except open friend, I guess.
Open what?
Not open friend or acquaintance.
Open pet?
Sorry?
Open pet?
Yes, open pet. There's also a course feedback form that I posted, which is just a good way for me to know what's working and what's not. Completely anonymous. If the number of responses equals the number of people in the class, I'll give some form of extra credit, even if the responses are like one word each. It's just 3 questions, but it's just good practice to do that for new professors like myself. Okay, so that's logistics. Let's get right back into it. So last time we introduced the concept of likelihood, and just from an intuitive standpoint, we discussed that if you have a data point and 2 distributions, where this is the PDF of a normal distribution with certain parameters, and this might be the PDF of a normal distribution with different parameters. Just from a conceptual standpoint, it's much more likely that the blue distribution parameters fit that one data point than the red distribution parameters. And then we, using that intuition, came up with an equation for likelihood of any model's parameters given the data, where X here is the collection of data, and that's going to be equal to the PDF distribution value of the first data point given the particular parameter values you're evaluating, times the second one, times all the way up to the final data point. And we're using the independence assumption here so that we can just multiply these out. Each data point is independent. It's a common assumption in machine learning. We then discussed that in practice, people, when implementing likelihood or in general probability calculations on a computer, tend to take the log of the likelihood or the log of the probabilities, and we'll see that repeatedly in this class. And the reason for that is, first of all, the log of a times b, we discussed this last time, is equal to log of a plus log of b. So this could then be extended out to log of that first data point's likelihood plus ... plus the log of the final data point's likelihood. And the reason we can do this, and we'll see this again and again, including today, is that the log of any function increases and decreases the same as the function itself which is useful when we're taking the max or min of something, because we just care about where is the max or min, rather than necessarily what the exact max or min value is. And we'll see that a little bit more concretely in a second. So then we talked about maximizing likelihood as a way to do machine learning. Maximum likelihood estimation, often abbreviated as MLE, which is not machine learning engineer, but related, I guess, where we perform the regular optimization problem of taking the derivative of the likelihood with respect to the model parameters, setting that to 0, and solving for the model parameters, which is just a regular optimization problem. I'm just recapping to set the stage for the rest of class. And in practice, this is the same as, so in practice, people solve the log of the likelihood. So the derivative of the log of the likelihood with respect to theta equals 0 for theta. And the reason is twofold, where both of these reasons are required to do this. Because one, when you multiply many likelihoods, it'll underflow on the computer, or many probabilities, or any fractions between 0 and 1, and you multiply a bunch of those, the computer can't represent that many zeros in a decimal number. So because many fractions multiplied will underflow. Just think about how many zeros there are in 0.01 to the 100th power, and that would be a likelihood with only 100 data points, a tiny data set, and yet even with that tiny data set, you can't represent it in a computer. So that's one reason. And the second property is writing it up a little bit more mathematically rigorously. The argmin, which is a new thing that I will define in a second, but the argmin of any function is equal to the argmin of the log of that function. So this is a new notation, argmin, but we're going to use it a lot. And it's really just writing in mathematical notation a concept that we've already talked about a lot in class, which is that when we say, and this is not just notation that I'm making up, this is common math notation, so you're kind of learning that as we go, which is cool. But argmin with respect to theta of f of x can be read in English as the value of theta which minimizes f of x. And then there's a similar argmax, which is the same thing, but for max. And so this is really what we're already trying to do from gradient descent, right? We want to find the values of the model parameters that minimize the loss function. Yes?
I guess I'm just a little confused. When you why? Okay, so I understood all of this, but then when you mentioned argmax, I was confused. In which situation would we want to find argmax?
When you're trying to maximize something.
But not in this case, right?
Well, in this case, we're trying to maximize the likelihood, so we will want to find argmax as well. I can write it out if y'all want. Yeah, I mean, it's the same for min or max. Let me just write that out. Oops, wrong thing. So just to be super thorough, same holds for arg max. And you can, for example, draw out y equals x squared plus 3 and see what happens if you take the log of that. And you'll notice that the value of the x-axis that results in the minimum doesn't really change.
Wait, arg max of f of x equals arg
Oh,
log
thank
theta?
you. Yes, I was talking and writing at the same time. Thanks. Arg min equals arg min. So if you just...
We want to make them both
Max,
Oh,
right?
yes, thanks. Arg max, arg max. So arg max of something is equal to arg max of log of that something. Same for arg min. Okay, so using that, what we want to prove now is this big takeaway that we ended class with last time. So the big takeaway for linear regression maximizing likelihood is equal to minimizing our loss function that we've been using so far for linear regression, mean squared error. So we're going to see that today, why that's the case. And again, you're not going to be asked to make a new proof in this class, but this is just for your understanding of why this is. It's kind of cool. So let's draw a linear regression again. And so as we all know from linear regression, we find a line of best fit. So x, y, line of y hat. And we have a bunch of data points. And writing out our y hat equation. This should be something you can do in your sleep now at this point because we've done it so many times. So one way we can model this situation is to say that the true value of the data point is equal to the predicted value plus some error. So that's kind of like a epsilon signal representing error. So let's write a comment. I'll use a hashtag, so it's like a Python comment, just to write this in English. So the true data is the predicted line plus some error. And we can model the error as being sampled, this is new notation, but sampled from a normal distribution where the mean is at 0 and that has some standard deviation sigma and variance sigma squared.
What is that symbol, that sample? What's that?
This one?
Yeah.
This is sigma. It's
Capital sigma?
I think this is lowercase. And it represents...
No, I mean the one above it, I'm sorry.
Oh, epsilon.
Epsilon.
Yeah, these are just kind of, it's not super important for this class, but it's just the common notation used in math. So,
Trying to figure out which symbol
so
to use.
so writing this in English, assume the error is normally distributed with mean 0 and variance sigma squared. Variance is just the square of the standard deviation. Don't worry about that for this class, but if you took statistics, you would already know that. So a way to write this more compactly, these two things is to just say that y is sampled from the normal distribution with mean y hat and our variance sigma squared or standard deviation sigma. To understand this kind of visually, let's go back to our drawing and let's think about how the error is distributed across the predicted line. So if we do find a line of best fit, then we can assume that the error is roughly normally distributed around that y hat. Does that make sense? So that's what we're modeling here. We're saying we have our predicted line and the actual values of the data point, so y, are normally distributed around that y hat. So that's, we're just writing that in math form. So now going to our log likelihood calculation. This is where the math gets ugly and not super important, but the log likelihood using that ugly equation for the normal distribution from last class can be written as the sum over all our data points, and it's the sum because we're adding up the logs. So the sum of the logs, that's just because we're, again, taking the sum of the logs computationally of that ugly normal distribution equation. So I'm going to write it out, but again, details aren't super important in terms of the 2 pi and sigma squared, not really critical.
Could you repeat the normal distribution for earlier?
The what?
The normal distribution, is that just for the arrows?
So the error is normally distributed, and because that error is part of this y equals y hat plus error equation, therefore y is normally distributed with mean y hat and with the same distribution of error as the error function. There's just two ways of writing the same thing, just with two equations or one equation. So back to writing our log likelihood. Where we're basically modeling let me write it with red. So this is the likelihood of our parameters, which would be y hat and sigma squared, given our data in this case, which is y. So like that. So we're just plugging that in. And
Question.
yes.
How come you don't write e to that thing over the root? Why do you always say 1 over the root times e?
Yeah, see, this is why I don't want to put the math. Don't worry about those details.
I'm just curious, why do you always write it like that?
It's just a way to write it. So using algebra, we can simplify this to this, which is the equivalent using some log rules. Again, details not super critical. And this is why they're not super critical, because remember that we're trying to, for maximizing the likelihood, maximize this equation in terms of theta. So we're taking the derivative, partial derivative of this equation with respect to theta, using our maximum likelihood procedure. Take the derivative of the likelihood, set it to 0, solve for theta. So we're solving for theta, and because we're taking the partial derivative with respect to theta, this whole term is a constant in terms of theta. So we could kind of ignore it because it's just a constant. You take the derivative of a constant 0, so not important. And similarly, we could ignore this term 1 over 2 sigma squared because going back to the argmin of f of x is equal to the argmin of a constant times f of x. So just like you take the log of it, if you multiply it by a constant, that's the case. You could play around with x squared plus 1 and see what happens if you multiply it by a constant. You could see that the minimum x value doesn't change when you do that. So when we do that, I think you're probably seeing where this is going now. Solving the log likelihood, maximum likelihood estimation, so solving the partial derivative of the log likelihood with respect to theta equals 0 for theta is equivalent to solving what's left of this term, which should look pretty familiar, the sum of our data points of y minus y hat squared with respect to theta equals 0 for theta. And therefore, our maximum likelihood estimate for the parameters, and this is just a common math way of writing maximum.
What's that thing in the denominator? Is that the partial with respect to theta?
Yes.
Okay, again.
Maximum likelihood estimate for theta.
Professor, what is the base of our log? Ether? E?
Yes, it's E. So you could write ln in this case. So that's why ln of E
Yeah.
cancels out. Yeah. Although technically it doesn't really matter because again it's just a constant, and when you argmin of a f of x is equal to argmin of a constant times f, so it doesn't really matter. But so the maximum likelihood estimate is equal to the arg max, because we're taking the maximum likelihood estimate of this term that looks pretty similar to mean squared error, y minus y hat squared, which is the same as the argmin over theta of, just remove the negative sign, because maximizing something is the same as minimizing the negative of that thing, of y minus y hat squared. And that is not quite mean square error, but this is the sum of square errors, which I'll abbreviate SSE. And to get the mean square error, from the sum of square error, we just divide by the number of data points. And again, this 1 over n is a constant. So therefore, argmin of all the parameters of the mean square error is equal to the argmin of the sum of square errors. And therefore, the maximum likelihood estimate is the same as minimizing the sum of square errors. Does that, I don't know, does that elucidate why mean square error is kind of a nice loss function mathematically? Who's like, I liked knowing that it's the difference between the predicted and actual value, and just stop there.
I'm not sure I could follow everything.
Okay. We'll look at the notes, and you won't be tested on this, but it's just good for a complete picture of what's going on.
So how come epsilon is always sampled from, so why is y hat minus six, minus plus, why is y hat plus epsilon?
Because y is the true values, the data points, and we're saying the true values are the predicted line y hat plus some error, and that error is normally distributed about that line.
But how do you
Best
know
fit.
that it's within 2 standard deviations of that line?
We're modeling the standard deviation. The standard deviation is a parameter to the model.
Oh, so we get to choose a standard deviation such that.
And it really doesn't matter what the standard deviation is because it gets canceled out later. So that whatever the standard deviation is, it doesn't affect this derivation. It's a constant in terms of theta.
I'll just put a note here that standard deviation is irrelevant, it gets canceled later.
Yeah, it's a constant in terms of theta. So that was how we derived mean square error. So now we haven't talked about the loss function for logistic regression yet. I haven't told you exactly what equation you would use. So I want to use the other distribution we learned about last time, the Bernoulli distribution, to derive quickly, hopefully, the loss function for logistic regression. And then all you have to know is that that's the loss function for logistic regression. But this is how it's derived. So, yes.
I couldn't understand. Sigma is not a constant. Sigma is not constant.
Sigma is a constant with
Because you know y hat is over of sigma, so probably theta.
no, 1 over 2 sigma theta. Again, this is not going into it, but just briefly 1 over 2.
Right side, I'm checking.
Yeah, on the right side, it's 1 over 2 sigma squared is like constant times y minus y hat squared.
Yeah, and it times to y hat. Yes.
Yes, but then even when you multiply it out, it's still a constant times y hat.
Okay.
So this is for linear regression?
This is for linear regression.
Okay.
Okay, we'll talk about it more later if you want, but I don't want to slow down the class too much.
Okay, I'm just making sure that I understood that part.
So going to the likelihood of the Bernoulli distribution, recall that we said last time the probability mass function of the Bernoulli is this equation, and we gave an intuition as to why. So just reminder, this is the Bernoulli probability mass function, where again we can take the log of that likelihood, and that's going to be equal to the summation of the same equation which, using algebra again and last time, is equal to this. It's so much equations, and I'm kind of regretting now putting this in here, so maybe in future lectures I won't do this because it's kind of, I feel like it's bogging us down rather than teaching us stuff, but since we started it, let's just finish it. Okay, so that's what it simplifies to, and therefore the maximum likelihood estimation of that is equal to the argmax over theta of, just to go fast, of that, which is equal to the argmin over theta of negative times that, but I guess I'll write it out because that might be confusing, of negative summation from I equals 1 to n of y sub I log of probability sub I plus 1 minus y sub I log of 1 minus probability of I, where the average of this gives us what's called the categorical, or sorry, just cross entropy loss function, and that is the loss function of logistic regression, which is important to know at least by name when you're coding it, but this is the equation for that loss function. And so you would minimize this value, and I'm going to write the probability as y hat now, or the predicted probability. Times the log of 1 minus y hat. And so that equation is the loss function for logistic regression. So whenever you hear people say you should use cross-entropy loss for logistic regression, the reason is because the cross-entropy is by a factor of 1 over n, the maximum likelihood estimation of the Bernoulli distribution, which describes what's happening in binary classification. Well, you have a probability of the event happening, where 1 minus that is the probability of it not happening. And I hope that's pretty clear from the homework 1, where the output of the model is the probability of that prediction. So now we have our loss function for logistic regression, which generalizes into multi-class. So I'm not going to derive it, but you might want to know how might you use logistic regression to predict between multiple categories instead of just binary categories. So all of these topics generalize to the multi-class. So the generalization of cross entropy loss to multi-class classification is basically a summation up to the number of classes of yi times log of yi hat, where C equals the number of classes. And just so you have everything you need to do logistic regression. So for multi-class logistic regression, instead of doing the y equals sigmoid of that linear equation, we do y equals softmax, which is a function we'll come back to, of the linear equation. Where the softmax equation of the ith class is equal to e to the power of the input times the summation over all the classes of e to the jth class.
Do we need, so that's, in the top it's e to the what I?
To the a sub I. I mean, it could be anything. Maybe a with my handwriting's hard to read, so I'm going to do it as x. Maybe that's easier to read. And it's kind of intuitive, just like with sigmoid, because you could see this equation's going to give a probability distribution, because if you're summing over e to the power of all the outputted values, numbers, and you essentially normalize by that, then, for example, let's say your linear outputs, I think it's best to see this with intuition. So let's say you ran this linear equation, and for each of the potential classes, and you get -3, 4, and 9, then the softmax of -3 is equal to e to the -3 over the summation of e to the, well, I don't need to write summation, just write out the sum. E to the -3 plus e to the 4 plus e to the 9th. So we're basically normalizing by the sum, and that's going to give us the probability of that class. Same for the next class.
So are those to put in the brackets the predicted outputs?
Of the linear equation, of the theta 0 plus theta 1 x1 plus ... Any other questions? Okay, we'll revisit this when we cover neural networks. This is really a sneak peek of neural networks, because something I haven't told you in this class, which is really cool in my opinion, is that you've been secretly learning about neural networks this whole time, because linear and logistic regression are neural networks. They're just really, really the simplest possible neural networks you can have. And so at this part of the class, we're going to switch over to a bunch of what are called non-parametric models, models where you don't use gradient descent to find them. You often use probability or other things that we'll learn about. So they're non-parametric because you're not learning parameters of a model. But it's not like we're going to throw away all this intuition we've built up kind of ad nauseum on parametric models, because when we do neural networks in the second half of this course, you'll find that neural networks generalize this concept, all the concepts we've been talking about in the class. So we're going to put away linear and logistic regression for several weeks and move on to a bunch of other popular learning algorithms. We use linear and logistic regression as a way to learn about the basics of machine learning. So
Is linear regression just basically drawing a line to the data and figuring out the best fit line?
yes, exactly.
Okay.
Yeah, just like we talked about in class 2. So let's go and start with, after all that math, it's kind of exhausting just to write all those equations, like my hand's kind of tired. So I want to give you a really easy algorithm that's non-parametric. So this one is gonna be, there's a homework question on it for homework 3, but this is actually a really intuitive algorithm, probably even more intuitive than linear and logistic regression, if that's possible. It's called K nearest neighbors. I didn't give this to you as the first one because I didn't want you to think that the whole class would be as easy as this algorithm. But the way it works is that let's say we have our data set that we're trying to classify. I'm not even going to give an example because I think you understand this idea of classification now. What we do in K nearest neighbors is to find so let's say we got a new data point here. That's the one we're trying to guess, or let me label it as a question mark to indicate we don't know the class. The algorithm is the following. Find the K, where K is a hyperparameter, nearest neighbors, as the name suggests, of the point in question, and classify as the majority. And that's basically all there is to it. So for example, that's one neighbor, that's a second neighbor, that's a third neighbor. So with K nearest neighbors with K set to 3, we'd classify it as the green category. The main interesting point about K nearest neighbors is that the choice of K matters. And let's show an example of that. And for those just reading the notes, K is a hyperparameter. So we're learning a bunch of hyperparameters as we go. Here's another one. Here's an example of how the choice of K could affect the outcome. So drawing that same, actually a slightly different data set. But
So it is literally given a point in space, which points have the closest distance to it.
yes, exactly.
So there's no like hidden. So basically you could just iterate through all the points and then calculate the distance and do it brute force it.
Yes. So if we said, actually, let me draw this a little closer. So let's say our question mark was here. So this would be the first nearest neighbor. This would be the second nearest neighbor. And this would be the third nearest neighbor. So as you can probably see, if k is equal to 1, that returns green circle as the output class, whereas if k is equal to 3, our algorithm returns the blue box. So that's all there is to k nearest neighbors. Any questions on it? Yes.
What qualifies a point as a neighbor? Like, so does it just calculate the closest point in the vicinity?
Yeah.
Okay, another question I had was, how do we know what value of k is the best for this type of classification?
You should use hyperparameter tuning like we talked about, which you should do in homework 2, and which we talked about in the last coding exercise lecture. So basically see what works best, but in a systematic way, ideally using grid search. Yes?
What happens if I have like a cool K of 2 and the distance is the same?
Sorry?
Let's assume like K is 2
Oh, a
and
tie,
the
yeah.
distance between two classes is the same. What happens?
I think you should only set k to be an odd number to avoid that situation. But you could arbitrarily break the ties, for example. Any other questions? K nearest neighbors? Okay, and of course this generalizes to multi-dimensions. So, x1, x2, x3, x4. It's the same thing, just finding the nearest neighbors in 4-dimensional space. Or more generally, n-dimensional space. This is a parentheses. N-dimensional space where n is the technical term is input dimensionality, but that's kind of redundant. N is the number of Okay, so now you have everything you need for questions 1 and 3 of homework 3. The next topic is another parametric learning algorithm, which we're gonna spend quite a bit of time on. So another one is called naive Bayes, and we hinted on this last class, or 2 classes ago, I believe.
Are we skipping decision trees?
We will go to decision trees after naive Bayes. And naive Bayes is for the coding question in your homework. So let me signify that this is another section. Okay. So we learned all this probability, and we learned Bayes' rule, which is from last class, that the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. But the way we wrote it last class was the probability of A and B divided by the probability of B. These are the same things. We're just expanding out using the and rule from last class, the numerator. So 2 ways of writing the same thing. And so for classification, what we're interested in is modeling the probability of each output class given the data. So using Bayes' rule, we can write that as the probability of the feature values given, or times the probability of each output class divided by the probability of the data itself. And with that model, it's pretty easy to classify. So we'll talk about training, but once we know these probabilities, then classification is simple. So I'm going to use a really common example for naive Bayes. This is spam classification. This is kind of the example everyone uses for naive Bayes, where you have email text and you want to classify it as spam or not spam, which is pretty useful, of course. And so we're going to learn this in the context of spam classification, which is also what you code in your homework. So to classify, very simple. We just use an if statement. So if the probability of the ith data point being equal to spam given the data point itself is greater than the probability equal to not spam given that data point, then we return a prediction of spam. Otherwise, we return a prediction of not spam. So intuitively, this makes sense because it's saying if the probability that the data point's label is spam, given what the data point is greater than the probability that that data point's label is not spam, given what that data point is, then we return spam. Otherwise, we return not spam. It basically reads as English, what you would expect a classifier to do. So the classification part's pretty easy, but any questions on that before we go to the training part? This one's pretty important to understand for both the homework and the exam.
So you said that if y equals spam, it's more likely to be spam than not spam. But do those spam and not spam, those probabilities add up to 1?
So we're saying that
Because the probability of it being spam plus the probability of it being not spam have to be 1.
okay.
Is that true?
Yes.
Okay, so those are.
So you could also just say Py equals to spam is greater than 0.5, you return spam. Right?
Yeah, you can, but in practice you don't do that because it's kind of a pain to calculate this denominator of Bayes' rule. and you don't really need to do it because the denominator is the same for the data point regardless of which class you're looking at. So for the homework, I don't make you calculate the denominator, even though that would give you an interpretable probability, because that would be a lot more coding. So you're welcome. All you have to do is calculate the numerator, because you know, the probability, I mean, if you think about it, the numerator is the only thing that has the label in it. So if you're evaluating a data point for different possible labels and seeing which label probability is the highest, the data point doesn't change. So there's no point in calculating the numerator if you're just comparing what's greater. So in practice, no one actually calculates the denominator. Any other questions on the training process? I mean, classification process, once you have the probabilities.
So in homework 3, question 5, you're supposed to put in the correct probabilities.
Mm-hmm.
And where do we get those probabilities from?
Good question. So let's go to the next section, which will address your question, which is how do we train? Where I'm putting train in quotes, because we're not really training it in terms of like gradient descent. But we're using a training set still. So what we want to model is the probability that we get, we want to evaluate the probability of spam and not spam. So we could write out the probability just of spam given the data point, which is this first term, as using Bayes' rule, the probability of the data point given that yi equals spam times the probability that the data point equals spam divided by the probability of the data point. And so to get the probability that the data point label is spam, let's say we look at our entire data set, we could simply write a for loop or whatever to calculate the number of spam messages divided by the total number of messages. And that gives us that probability on the right-hand side of the numerator. Okay, so we basically want to calculate each of these probabilities that make up the Bayes equation on the right-hand side. We have probability that yi is equal to spam. You just look at all the data points in your training set and see how many of those have the spam label. And then to get the denominator, which again, you technically don't need it for the homework, but if you wanted to calculate it for fun, or to, importantly, in some cases, to return a interpretable probability, then you would calculate the number of emails with these features, xi, divided by the total number of messages. We'll do a concrete example after this so you can fully put this to practice. So the probability, so this last term up here, let me just erase that for when I export these notes. But the probability of the data point values given that the label is equal to spam is equal to the number of spam messages with features xi divided by the number of spam messages. Because we're conditioning on yi being equal to spam, or the label being spam. So we're dividing by that because the only points we're considering are those that are spam, and we're counting the number of points with features xi that are also spam messages.
I guess I'm more confused. So y here is just a binary thing, spam or not spam?
Yeah, for this example.
Okay, so what is x then?
X is the data. So I'll give you a concrete example.
Yeah, 'cause I guess if I
The
check-
email message.
Okay, because that's what I figured, but then when you wrote features spam messages with features
Yeah, good question. So the features could be many different things. What we're gonna do in this example today, and also for the homework, the features are the presence or absence of a word in the email text. But you could imagine more sophisticated ways of representing your data. But for the homework and for today, we'll work with that. So the xi are the presence or absence of each word. So let's work through an example to make this clear. But just quick comment. The naive, you're probably wondering why it's called naive Bayes. The naive in naive Bayes comes from the fact that we're assuming that all features xi are conditionally independent given label yi. So let me show you what conditional independence means through an example. So this is all kind of abstract, but I think it'll become super clear once we walk through an example. So let's say you wanted the probability that the word hello is in your email and the word Vicodin is not in the email and the word 340 is in the email, given that it's a spam message. That would be, if under conditional independence, would be the probability that hello is in the email given spam times, so we're multiplying them out, but they're only an independent conditional on spam, times the probability that Vicodin is equal to 0 given spam times the probability that 340 is in the email given that it's a spam message. So that is the conditional independence assumption, which could make sense. It could be a reasonable assumption, like each word is independent of the other given the category. It also might not be, because some words are correlated to others. But for the case of naive Bayes classification, it's naive in that it assumes that each word is conditionally independent, or more broadly, each feature is independent of the other features.
So when looking at the notebook, something like probability of word free exists given that it's spam. To get this,
We'll get there. Let me work through an
I
example.
thought
and
we
then-
were already past there, so I just wanted to
No, we'll get there.
Quick question.
Yes.
I'm sorry, so in this example, we're saying that if the email contains the words hello and 340, then it is spam. We're saying it's not spam.
No. We're not doing anything. We're just saying the probability that it has the words hello and 340, given that it's spam, is equal to the probability that it has the word hello, given that it's spam, times the probability that it doesn't have the word Vicodin, given that it's spam, times the probability that it has the word 340, given that it's spam.
So we start by knowing that this is a spam message we're looking at?
No, we for the training data, yes, but when you're classifying, no. So,
So right now this is training data.
yes. Okay, so let me just go to an example. There's a few more theory stuff I wanted to cover, but I think this will make a lot more sense with an example. So let's say we have our training data set. Let's even call it, no, I was gonna say let's call it xtrain, but that's okay. And we have feature x1 and feature x2. For example, the presence of word x1 and the presence of word x2. And our training data set in NumPy would look like this. And the corresponding Y labels for, let's say, spam and not spam look like this. Trying to make sure these line up close enough.
Sorry, what's x1 next to again?
The presence of, so we could say x1 is the presence of word x1. I don't know. I won't specify the word for this example. And x2 is the presence of word x2, just abstractly speaking. So let's say we want to classify, a new data point, x question mark, which has 1, 1. That's the data point we want to classify. We don't know what label to give it. So how would we calculate this using naive Bayes? Well, we would evaluate the probability that yi equals 0, given that the x data point, well, is equal to 1, 1, which is, just looking at the numerator, going to be proportional to the probability that x1 is equal to 1, given that y is equal to 0. I'm going to remove the I subscript just to make things less confusing. Times the probability that x2 equals 1, given that y equals 0. times the probability that y is equal to 0. That's just the numerator of the naive Bayes equation, equals, well, if we look at it, what's the probability that x1 equals 1 given y equals 0? Well, there's 4 data points where y equals 0. What's the number of data points where x1 is equal to 1? Well, all 4 of them are 1 when y equals 0. So this probability is 1 times, let's do the same thing for x2. What's the probability that x2 is equal to 1 given that y is equal to 0? Well, there's one of these 4 data points where y equals 0 has x2 equal to 1, so that probability is 0.25. And then what's the probability that y equals 0? Well, 4 out of the 10 data points have y equals 0, so that would be times 0.4, which comes out to be 0.1. So we've evaluated the case where it's not spam. Now let's look at the other probability. So doing the exact same thing, it's going to be proportional to the probability that x1 equals 1 given that now y equals 1. Sorry, I'm trying to distinguish the ones from the given signs, but it's kind of ruining the handwriting. Probability of x2 equals 1 given that y equals 1 times the probability that y equals 1, which is equal to, well, for this first probability, how many data points have y equals 1? Well, that's the top. 6. So out of those top 6, how many have x1 equals 1? Well, I see 1, 2, 3 of them out of 6. So the probability is 0.5. Same thing for x2. 1, 2, 3, 4 of them. So that probability is 2/3. Times, what's the probability that y equals 1? Well, that was 6 out of the 10 data points. And that is equal to 0.2. So because 0.2 is greater than 0.1, classify 1 as y equals 1, or spam in our example. Did that example help clarify all this? Okay, there's more abstract stuff I want to cover, but let's just get the example, and I think that makes things more clear. Any questions on this?
So is this how spam filters sort of work?
Not anymore. They're a bit more sophisticated these days, but
Can you scroll up just a little bit again? Sorry.
yes.
Just the table.
Yes. And so you're gonna basically, for homework 3 in the coding section, do this procedure, and you could imagine you have your x and y data, and you're counting out of, for example, you basically compute each of these probabilities by looping through and only considering when y equals 0, counting how many times x1 is equal to 0 and how many times x1 is equal to 1 divided by the number of times where y1 is equal to 0 or 1. And so you're calculating all these probabilities, basically doing the procedure I just verbally said for y'all in code. But you can imagine how this would be pretty straightforward to code relatively. You're counting things. So for loops or list comprehension in Python. And then you just multiply them out together and see which value is greater. And the coding notebook for homework 3 should walk you through it pretty closely. And yeah, we'll continue on IBase on Tuesday.
Question.
Have a good weekend.